So I have an interesting system over here. I have two compartments. On the left compartment, I have a gas that is at a temperature of T sub A. And on the right side of this, I have gas that is a temperature of T sub B. And they are separated by a wall of depth D, or I guess you say of thickness D, and the contact area of the wall, or the contact area of the gas onto the wall, that area is A, and I'm just drawing a section of it. We're assuming that these two compartments are completely separated. Now, what I am curious about, and we're going to assume that the temperature on the left is higher than the temperature on the right, and so because of that, you're going to have a transfer of thermal energy from the left to the right, and that thermal energy that gets transferred, we call that heat, and we'll denote that with the letter Q. I'm curious about how does the rate at which heat is transferred, or so how much heat is transferred per unit time, that's the rate at which heat is transferred, how would that change depending on how we change these different variables? So for example, if our contact area were to go up, what would that do for Q over T? Well, then Q over T would also increase per unit time, because I have more area for these hot air particles or hot air molecules to bump into, and they'll heat that wall, and then there'll be more heated wall to heat up the colder air particles. So in that case, our rate of heat transfer would also go up. Well, what if we, and obviously if I made my area smaller, maybe I should just write that explicitly. If I made my contact area smaller, then my rate of heat transfer would go down, and that feels like common sense. Now, what about the thickness? If I were to make the thickness larger, if I were to make this a thicker wall, what would that do to my rate of heat transfer? Well, then I would have more things that I would have to heat up to get it to a certain temperature which then can heat up the particles on the right. And obviously this is a continuous process, it'll always be happening, but there'll just be more stuff to heat up, and it's going to take longer, and more of that kinetic energy, that average kinetic energy, is going to get dissipated in this wall. So if this wall becomes thicker, then the rate of heat transfer is going to go down. Or if the wall became thinner, if this depth decreased, then the rate of heat transfer would go up. So you can say the rate of heat transfer is going to be inversely proportional to the thickness of this wall. Now, what else could we think about? Well, we could think about the temperature differential. The temperature differential, that's T sub A minus T sub B. Well, if this temperature differential were to go up, well, what's going to happen? Well, it's common sense that, well, if this is super hot over here, or this is way hotter than what we have on the right, well, we're going to have more heat transferred. So the rate of heat transfer, you're going to have more heat transferred per unit time. Your rate of heat transfer is going to go up. And likewise, if this differential were to go down, and you could take the extreme case, if there was no differential, if T sub A was the same as T sub B, then you would have no net heat transfer, frankly, in any unit of time. So it makes sense that the rate of heat transfer is going to be proportional to the temperature differential. So how can we encapsulate all of this intuition into maybe a formula for describing thermal conductivity, for thinking about how quickly this heat will be transferred, the rate of heat transfer? Well, we could say the rate of heat transfer, and this is really, hopefully, comes out of a little bit of common sense or an intuition of what would happen here. The rate of heat transfer, I could say it's going to be proportional to, well, what are the things it's going to be proportional to? It's going to be proportional to the area. The more surface area we have on this wall, more contact area, the more heat we're going to have transferred per unit time. So it's going to be proportional to that contact area. It's also going to be proportional to the temperature differential. So let's multiply this times the temperature differential. So T sub A minus T sub B, and it's inversely proportional to the thickness of the wall. So all of that over the thickness of the wall. And now another thing that you might be saying is, okay, I have this proportionality constant, but wouldn't this be different for different materials? For example, if this was a metal wall, wouldn't this conduct the heat quicker than if this was a wood wall? And you would be correct, a metal wall would. And so this K right over here, this is dependent on the material. So what is the wall made of? So material of the wall. And you can actually measure this thing, and different materials will have different thermal conductivities, which this variable right over here would actually represent. So going through a little bit of intuition, we were able to come up with what looks like a fancy formula, and you will sometimes see this formula for thermal conductivity through a solid barrier, but it really comes out of hopefully common sense. The rate of the amount of heat transferred per time is going to be proportional to, and the proportionality constant is going to be dependent on the material. Styrofoam, for example, would be very low here. That's why coolers are made out of styrofoam. And it's going to be dependent on the area. It's going to be proportional to the area, the temperature differential, and then inversely proportional to the thickness. So if you wanted to really insulate something, you would want to minimize surface area, and you would want to maximize the thickness, and you would want to have something with a very low thermal conductivity. So a thick styrofoam wall that's maybe shaped in a sphere might be a pretty good container for keeping something hot or for keeping something cool.